Welcome to Mechanics of Composite Materials. We'll be discussing classical plate theory. So, to really explain what we're trying to do, when you're modeling large scale structures, if you were to model it with finite elements, you may have to use 3D elements, which are quite computationally expensive. Say you have the skin of an aircraft, which is fairly thin. Instead of modeling the through thickness direction with a lot of elements, we will model it a little bit differently. What we're going to do is take the 3D structural representation and idealize it as a surface. Okay. And what we're going to do is track the deformation of this plate by following the mid surface of that plate. And so we've simplified then by doing so a 3D finite 3D plate into a 2D surface, which now what you can do is if you were to model the aircraft, you would just model this mid surface, and that is representing the 3D behavior of the structure. The question is, how can we do this simplification in a way that's mathematically correct, physically correct? And again, since that's an assumption that we're making, there are going to be some fundamental issues with the equilibrium equations. So, classical laminated plate theory, we're going to start with the displacement assumptions, the strains, the stresses, and then we're going to go into the constitutive law. So, these are the areas that we're going to cover today as far as mechanics of materials. So, classical laminated plate theory, what we're trying to do is we're trying to track the mid surface. This mid surface is going to have some in-plane deformation. So you have here the deflection in the x direction, the deflection in the y direction, the deflection in the z direction, and as you can see here, there's a superscript here which really symbolizes the fact that we're tracking the mid surface. That's really what we're tracking here. And again, tracking the mid surface does not mean that we're not ignoring everything else. We still have to somehow consider the whole plate. Okay. And so classical laminated plate theory was initiated by a gentleman whose name was Kirchhoff. So we also call this theory Kirchhoff plate theory. And the idea that we have here is that when a plate undergoes deformation, when a plate goes under deformation, that the normal to the mid surface will remain perpendicular to this mid surface. So, in other words, I can deform this plate as much as I want, but the normal to the surface will remain perpendicular to that mid surface. Okay. And so it implies then that the deflections vary linearly through the thickness. So that's one of the assumptions we're making in this theory. So if I were to look at z equals 0, I recover then the deflections at the mid surface. This mid surface is at z equals 0. Okay. But if I look away towards the top of the plate or bottom of the plate where z equals h half, assuming that the plate is h, then z equals h half is the top surface of the plate, z equals minus h half is the bottom surface of the plate, then the deflections at any point through the thickness of the plate is given as a deflections of the mid surface, and here you have minus z times these slopes. Okay, and while we'll talk more about these slopes, but as you can see, when I put z equals 0, I recover the deflections of the plate at the mid surface. Anywhere else, what I have here is the contribution of the mid surface and then a slope times z. Okay, obviously w here is the through the thickness direction. What we're saying is that doesn't matter where I am through the thickness of that plate, I'm going to assume that every point through the thickness of that plate follows the outer plane deflection at the mid surface. So whether I'm at the top of the surface or bottom of the surface, it doesn't matter. The outer plane deflection W will be equal to the deflection of the mid surface of the plate. That assumption makes sense because if you have a thin plate and you deform a thin plate, you don't expect significant changes to the thickness of that plate. As a consequence, doesn't matter where you are in the thickness of that plate, the deformation through the thickness will be equal to the deformation at the mid surface of the plate. Okay. And so the question is why we arrange the equation in this manner. Okay. And I will explain that a little bit more, but I want you to remind you that we're assuming here that when the plate deforms and the plate is thin, that the normal to the mid surface remains normal after deformation. That's a very important assumption that works very well for thin plates. So then the normal to the mid surface remains normal after deformation. That implies that the transverse shear strains are zero. And the reason that is the case is because we just told you that Z, which is normal to the surface, that that's going to stay perpendicular to the mid surface of the plate, which means that Zx and Zy, that angle is not going to change. Therefore, the strain, which we had discussed previously, these strains are the transverse shear strains. These transverse shear strains are zero. And so when I plug in the definition of transverse shear strain, that is the derivative of u respect to z plus the derivative of w respect to x. And what I see here is that the derivative of u respect to z of this equation is really this coefficient here. So that's negative w at the mid surface respect to x. That's what you got there. And then plus the derivative of w respect to x, and w, we said that doesn't matter where it was, it's w naught. So therefore, I have this term that goes there, and you can see that it automatically cancels out, and I give zero. It gives zero. The other transverse shear strain similarly switch x and y, and you get the same answer. What we see here is that with this assumption we made, it tends to be a pretty good one because this we're able to show you that on these assumptions we can get these transverse shear strains equal to zero, which is an important assumption. So now let's try to explore to see what is going on with this plate. So let's look at back at this plate here, and I'm going to look at it from the side. So such that x goes this way, the thread thickness goes in the z direction. The plate goes from plus h to minus h, and then I'm going to say, okay, well, this point here B moved to B prime and amount U superscript 0. And that is the deflection of the plate at B. So if I put Z equals 0, what I get is that this goes away. And so the deflection point B, it is really just a deflection U superscript 0. So there you go. It moves to this point. So then what is going on next is that the plate deformation is driven by the second term here. And so if I look at the slope at any other point, so say I have a slope of derivative of w with respect to x of that plate, clearly the plate is tilted, okay? And you can see here that this amount is derivative of w with respect to x. And so that does contribute to deflection in the negative direction. And you can see that that's occurring right there, as you see it there. Okay, so as you can see, when z equals minus h half, which is at the bottom of the plate here, and I know I realize I have it inverted, so z equals h half is top of the plate, z equals minus h half is bottom of the plate. If I put z equals minus h half into this equation, u gets augmented by the slope times the h half times that. And you can see that here. This deflection is a little bit greater when I look at point A prime. So point A moved a little bit more to the right. Likewise, when we look at point C move to the left, respect to B prime. And so that makes sense. Okay. So you can see here that I am able to track the plate behavior through the thickness if I just track the mid surface. And that will simplify the problem. And that's what we call this the classical plate theory. We've simplified the problem. And so, sorry about that. So here you can see that the W equals W naught implies that the derivative through a thickness direction of that deflection is zero, which is really the strain in that direction. So no thickness change implies no strain in that direction. So using these assumptions that we made, we can calculate the strains, the remaining three strains, because as you saw, this strain is zero, and these strains are zero. These transverse shear strains. And there are 6 components of strain. So I only have 3 to worry about. So that's epsilon x, epsilon y, and gamma xy. Epsilon x, epsilon y, gamma xy are strains in the in-plane directions of the plate. Again, z represents the out-of-plane direction, x represents the in-plane direction. And as you see here, is when I substitute what epsilon x is, which is the derivative of u respect to x, I can plug this equation into that. And what I get is derivative of u respect to x plus z times the second derivative of w respect to x. Okay? So you also get that for epsilon y. If you switch x and y, you will see that. And then gamma xy, you also can get something similar. Okay. So these ones here are called the curvatures of the plate, and these are the mid-surface strains. When z is 0, you recover the mid-surface strains, and then anywhere else in the through the thickness of the plate, you can get it by plugging values of z. For example, if I want to know what's going on the top surface of the plate or the bottom surface of the plate, I'll plug in z equals h half or minus h half, whatever what we're looking for. Okay, but notice how we've simplified the problem so that the strains are dependent strictly of deflections which only are depend on the xy coordinate system, and we have explicitly factored out z so that all the quantities depends on x, y, and z. So we simplify the problem quite a bit by doing that. And so there you go. So we have the strains can be broken down then into mid-surface strains and curvatures multiplied by z. And again, a lot of equations here. The important thing to understand is that the unknowns for this plate right now are u, v, and w at the mid surface of the plate. While before, in contrast, you will have not known u, v, and w, but for the whole plate. But now I don't know u, v, and w for the mid surface of the plate. We simplified the problem to track in just the mid surface. And by doing so, we have simplified the problem a little bit more. And so as we continue here, I will show you what's going on and what things do really mean. So given the laminate, you may have a strain variation, and the strain variation is always going to look linear. So as you can see here, there is a strain through the thickness, and the mid-surface strain plus z times the curvature. This means that given the mid-surface strains, given the curvature, the strain through the thickness is going to have a variation that looks like this. Okay. But if I have different plies and every ply has different lamina properties or modulus, then the stress is going to change as you go through the thickness. Okay? So that's an important consideration to understand what is going on with the strain distribution through the thickness. Is a linear distribution is what we're assuming, and then the stresses could vary depending upon what the modulus of each lamina is. If I have no curvatures, just stretching, meaning no curvatures, just stretching. So if I have no curvatures, then the strain, doesn't matter where I am, is the same as the one on the mid surface. So you're going to have stretching of that plate. If, in the other hand, I have no amount of stretching, I only have curvatures, then the strain distribution through the thickness is going to look like this. Okay. And then, the other hand, if I have stretching plus curvature, just add this plus that, and it is going to generally look like this. Okay. So again, it's important to understand what the strain is doing to the laminate. So we had previously discussed that there's three-dimensional elasticity equations. There's three governing equations that describe that. And that was derived from Cauchy's relationship. We use the second Newton's law, but the integral form of that. We use those two facts to come up with the equilibrium equations as you see them here. And we did that using the virtue of Gauss' theorem. And so note how all these deflections depend on x, y, and z. Okay, all the deflections do. But for classical plate theory, we were able to make it so that it depends just on x and y. Just to remind you, here it is what we've done. We have u, v, and w that depend on x, y, and z, but now we represented the deflection so that it's only a function of x and y, and z now is explicitly defined. So not only I have simplified having to find u, v, and w through the whole plate, and depending upon where I am, x, y, and z, now I have simplified the problem so I can find it. I only have to find the deflections at the mid surface, and those deflections only depend on the x, y, and x, y coordinates within the mid surface. So the question is, we had in 3D, we had these equilibrium equations, and the question is, what does that look like for 2D? Because I made some significant assumptions, and those assumptions were that the normal remains perpendicular to the mid-surface after deformation. That was assumption number one. And that the thickness direction of that plate is not going to change very much. And we already discussed that those assumptions make sense for a thin plate. And we came up with those strain deflection relationships. The question is, how do I come up with equilibrium equations that correspond to 2D? Because these are for 3D. Okay. And In reality is that we need to find a way of getting these governing equations so they're consistent with the assumptions we already made. And so we need to come up with new stress quantities that really represent the behavior for the mid surface of that plate. They're able to measure those internal forces. Recall that stresses are quantities that are reacting external loads applied to the structure, and those stresses can be drawn on a cube representative, and we can then determine what stresses are reacting these external loads. But now that I have a 2D representation that I'm looking at, if I went back, the 2D representation becomes a little more complex. What does it mean for this problem where we're now just tracking the mid-surface? So feel free to pause the video and see if you have an idea of what you can do to come up with the 2D equilibrium equations. It's a little trick, but I think once I show you the trick, you will say, wow, that's what it was. Okay, now that I gave you a moment to pause it. And if you did it, I congratulate you for being the king of equilibrium equations. So here's what we're going to do. We're going to take these equations and integrate these equations through a thickness. That is what we're going to do. So, and by integrating these equations, we'll find that these 2D like stress quantities will be compatible with the curvatures and midplane strains that we had previously discussed. So I'll go ahead and do that. I'm going to integrate these three equations through the thickness, minus h half to h half dz, where h half minus h half is the bottom of the plate, h half is the top of the plate. When I do that, I'm going to distribute the integral into each of these stresses, keeping the derivatives in the outside. You can see that here we've accomplished that there. But when I go to this particular term, I have derivative of the sigma xz dz times dc. Well, that integral is really sigma xz evaluated at the top or bottom of the surface. I can then distribute that to the middle equation here, and all you have to do is switch x and y to get this bottom equation. And then finally, I have this third equation. I can integrate that through a thickness as well. And this third term, again, experiences this simple evaluation of top or bottom of the surface calculation. So right now, what I've done is converted the 3D equilibrium equations into 2D quantities by integrating through a thickness. Okay. So this right here that you see here highlighted with a bracket, this right here is a type of stress. Okay, there is still a stress. We just integrated the stress through the thickness. We've also done that with each of these terms, and you can see that here. So it's 1, 2, 3, 4, 5, 6. And these are force resultants. We'll call them force resultants. And if I look at the units, if stress is psi, then these units are stress. Basically force per unit length. Okay, force per unit length. Why is that? Because I integrated the stress through the thickness, and so now I have this quantity that's force per length. Okay, so that's what we got there. These are, in fact, the quantities that react the external forces, but for a plate, not for the most general 3D, because for the most general 3D, it was a cube with stresses drawn on the cube that reacted the external loads. But when I simplify the problem to 2D, it is this, in fact, these forces here, they are the ones that react those forces, the external forces. So now when I look at the plate in general, the top surface here, the top surface is very unlikely when I apply tangential forces to top surface. And so as a consequence, sigma xz and sigma yz will be zero at the top and bottom surface. However, very likely, just like in an aircraft, you may apply perpendicular loading to that surface, that will be pressures. And as a consequence, sigma cz is basically a pressure applied at the surface. Now we're only applied at the top surface, not the bottom one, so therefore, we only carry one of these guys. Sigma zz at evaluated h half equals p. Because sigma zz at minus h half, there's no pressure applied on the other end. So the equations have indeed simplified into these two equations and this third equation. But we still have something missing here, and that's something related to bending, because these forces here, I'll show you later, but they really represent the in-plane forces, okay? The in-plane force quantity. So the idea then is to multiply by z, and what we're going to do now is multiply by z but these equations right here. So each row will be multiplied by z, okay? And then we're going to integrate through a thickness to be able to get the bending behavior. So here it is. I multiplied by z, integrated through a thickness, and I did it for two of the equations. And what I want you to focus on is this term right here, okay? So again, all we've done is taken the first two equations, these first two equations, multiplied by z, and then integrated through a thickness. And then I distributed the integrals into the integrand. And so I invite you to pause the video to kind of replicate what I've done. But here, what we have is this derivative, the integral from minus h half to h half z times sigma z alpha dz. And so this x has become alpha. And if you look at this, we can integrate this by parts. And integration by parts will result in this minus that, okay? And what we realize really quickly is that this is the shear force through a thickness. This quantity here becomes a shear force through a thickness. And that's also true for this case, okay? So this determines that. We already told you that evaluating this at the top part of the surface or bottom part of the surface will give you 0. So this is not present anymore. But this right here is Q. And so you can see here quickly that I found that this derivative altogether is Q. So then I have, for the first equation, I have that. For the second equation, I have that. And I want you to focus on this, the moment, okay? These are moments, right? And they have units of force somehow. But these are important quantities that these are the bending moments that resist the external loading conditions. So I can now plug these two equations into the third equation. So I had this equation here, the third equation here. I can plug in qx and qy into this equation. And what I will find is that this is a governing equation governing moment resultants. So this plugs into here. I get the moment resultant governing equation. And then I have these two equations which are related to force resultants. Okay. And we have defined already for you that nxx is the integral of minus h half sigma xx. Ny is the integral of minus h half to h half sigma yy. Nxy is the integral minus h half to h half sigma xy. And likewise, for the moment, is the same as this force resultants, but with the z multiplied by it. And so this is really what came down. Is this is the force resultant, this is the moment resultant, and what we want to do is relate this somehow to the strain relationships we had derived. And to do that, it's going to take some work. It's going to take some thinking. Okay. We also want to understand the physical meaning of these force resultants. So these stresses are the ones acting on the cube. What we've done is we've integrated these quantities through a thickness, and basically that will give me a 2D representation of what's going on because I eliminated z out of the equation by integrating this through a thickness. Okay. I did the same thing with the bending moment, and so I get this. And so what is going on here? I want to show you exactly what's going on. So nxx here, this nxx is the integral of minus h half sigma xx dz. So I've integrated sigma xx, which is pointed on this surface, is pointed in the x direction. And by integrating this from minus h half to h half, I'm left with nxx, which is at the mid surface. Nyy, nxy the same way. Nyy is acting in the y direction. NXY is acting in the shear direction NS. So NS is the same as NXY. This was from a different book. And then I have the bending moments that can be studied. And the bending moments will be MXX, MYY, and then torquing of that plate MSS, which is MXY. You can see here by applying the bending moment, you're going to torque the plate. And also for MXY here in this MS is the same as MXY also. And notice the units are force per length, and the moment resultants are force per length. Okay, so again, why is that? Because you're used to force being units of force, but it's not really a force, it's a force resultant because it's the stress really integrated to the thickness. And so how many quantities I have here? I have 1, 2, 3, 4, 5, 6. And so before I continue here, the thing I want to point out now is that this integral here from minus h half to h half needs to be broken up. So as you know, integrating from minus h half to h half can also be broken up in small integrals. And so if I have a laminated plate that goes from minus h half to h half, and I have all these plies that go from K1 to Kn, so n plies, laminated, The integral also can be written in this manner. Integral from k1 to n, summation of k1 to n, integral zk minus 1 to zk. This integral is equivalent to this integral looks more complicated. Sorry about that. Because we're trying to break up the integral into the integral between this point to this point plus the integral between this point to this point, which is the same thing as the integral from this point all the way to this point. But we have to break it up. And the reason we have to break it up is because the modulus in every plate is changing and the angles are changing. And we want to be able to understand the overall effective behavior of this plate. So that is the approach to use to get there. Now, that's for the force resultants. For the moment resultants, very similarly, as you saw here, this integral of the stress quantities is multiplied by z. So these integrals will be broken up into small integrals that correspond to each ply. So the integral for that one ply, second ply, and so forth. And I have n plies. So that's why I have a summation here. And take an example, the second ply goes from z1 to z2. So I'm going to have the integral from z1 to z2, calculate that, and add that onto the other integrals for the other plies. So that integral should be equal to this integral. Mathematically, they're the same. So again, I know this looks scary. I have this summation, I have this integral, but mathematically, there's nothing to be worried about because we're talking about the same things. This is the same as that. We just broke it up because we have many different plies. So in classical plate theory, we're utilizing. So now that I came up with this conclusion, I found the 6 stress resultants. These are the 3 force resultants and 3 moment resultants for a 2D plate. We have come up with the strain relationships for a plate, which again, those deflections only depend. The deflections are only depending on the XY position at the mid surface. And that's the key there. We already found in classical plate theory, if the plate is thin enough, we can make the assumption that the outer plane stresses are zero. If the plate is too thick, then this is not the case. But for thin plates, this is not a bad assumption. And why is that? Because the stresses through a thickness will not build up enough to be a concern. And so for thin plates, that's really all you have to worry about. It's a good assumption. So these 3 stresses become the ones that we need to worry about. So in the classical plate theory uses a constitutive law that we're going to simplify. So I want to focus then on the constitutive law now. So we already completed the idea of how to represent 3D stresses into 2D stresses, or stresses corresponding to a plate. But now we have to relate the stresses and strain. And so since these are the only stresses that matter, and this is a constitutive law for what we've done is simplify the constitutive law. This used to be a 6-component vector with strains and 6-component stresses. But since we've said that these 3 stresses are small and can be neglected, then the constitutive law can be simplified in this manner. So go back and look at the previous video lecture where we talked about 3D constitutive law. And there, this was a 6x6. But here, because 3 of the stresses are 0, we can reduce the strain stress relationship in this manner. And so pretend, so this 1, 2, these correspond to the principal material orientations of the ply. So think of this stress strain relationship. And we talked about that. We talked about this stress strain relationship correspond to the principal material orientations, while the X, Y, and Z here correspond to the edges of the plate, and the ply angles may not, the 1 and 2 and 3 directions may not coincide with the X, Y, and Z. The ply angles could be at some other angle relative to X, Y, and Z. So that's why it's important to really keep track of these different conventions going on. And what we're going to do, we're going to invert this and put it in terms of stress. So I can invert this fairly quickly. And once you do that, I'm going to take this strain divided by 2 and put the 2 here. It's the same thing. That'll allow me to do some coordinate transformations later on. So if I were to invert this in MATLAB or some code, what you will find is that Q11 is this, Q12 is this, Q22 is this. And as you know, these properties, these 4 properties come from the constitutive, basically testing to inform the constitutive properties. And we had extensive discussions about how these properties can be found, but these are the properties you will find. Once you have these properties, you can calculate Q11, Q12, Q22, Q66. And what is interesting is that these numbers are the same for every ply if we're using the same material system. If you're using a hybrid material system, then you could have different values of Q on one depending upon the material you're using. But for most applications, for the same material system, these four Qs should be the same from ply to ply. And so when I go back here, what is really changing from ply to ply is the angle. And so now my goal now is to somehow relate these stresses, which are stresses in a ply orientation other than the XYZ orientation. I want to relate these stresses here, X, sigma YY, sigma XY. These stresses, I want to relate them to the stresses in the principal material orientation. And so we can perform a coordinate transformation, and I've discussed extensively how to do that. But to summarize it, for for this reduced second order tensor of stress and second order tensor for strain, we can transform it using this equation. And so alpha becomes the ply angle. Again, if the ply angle is 0, then the cosine of 0 is 1. So this becomes 1, that's 0, that's 1, that's 0, that's 1. So the stresses x, y, and z and tau xy, the shear, in-plane shear, these in-plane stresses become equal to the in-plane stresses in the principal material orientation. That makes sense because the angle is 0. So this is the way you transform it. We're gonna call, and you can derive this using the formulas discussed in class previously. So we're gonna call this T bold. So that's T bold. I can then also transform the strain if I wanted to, and the strain will be equal to T bold this strain. So if you know the strain in the global orientation system, you can find the strain in the local material principal system. And the same for the stresses in the global orientation system. I can then calculate by multiplying by T, I can calculate the stresses in the principal material orientations. And again, these M and N are cosine alpha and sine alpha. We're using M and N to simplify the writing these matrices and make it less messy. So given these relationships, I can then transform this constitutive law and relate it to the global orientation system. So I know the stress in the principal material orientation system is T bold times the stress in the global orientation system. So that's that. And I know the strain in the material principal orientation can be related to the global strain with T bold that. And we just did that here. We showed you how to do that here. And so then all I have to do then is to pre-multiply by T inverse to get identity matrix here. So then now T inverse shows up here. And that's exactly what we saw. So as you saw, suddenly, miraculously, Q is defining the principal material orientation. But with these transformations, we're able to relate the stress in the global orientation system and the strain in the global orientation system. So we've been able to accomplish that. Now I can take this T bold, which was given here previously in this chart, and I encourage you to pause the video and kind of derive it yourself. So that's T bold. I'm going to take that, invert it, and I'm going to take T bold there, and I won't multiply all of that. And so when you multiply all of that, typically in the books we're going to find is that they're going to call this matrix, they're going to put Q1 bar like that. And so if I were to expand Q1 bar, note that this is the same for every ply if I'm talking about the same material system. The only thing changing is the angles. So this one and this one. Q1 bar becomes that, and you can find all the Qs that correspond to this matrix. So I'm able to then relate stress to strain using this matrix, constitutive law. And note how Q1 bar and so forth can be found by multiplying all this stuff. And that Q1 is known and the ply angle is known. So you can relate, if you know the strain, you can find the stress using this formula. Because this is a messy form, what people have done is make it a little bit easier to write it out. And it's actually useful for optimization. So Q1 bar can be written instead as U1 plus U2 plus cosine 2 theta plus U3 cosine 4 theta. And U1 and U2 and U3 are called invariants. Theta is the ply angle. And so Q1 bar can be written in that manner. And note that Q1, Q2, Q12, and Q6 are fully known. So U1, U2, and U3 are the same for every ply. And so Q1 bar only depends on that angle. And all these numbers are known for every ply. All other stiffness quantities corresponding to these matrices, this matrix right here, are provided here for completeness. And notice how, again, it depends only on U1, U2, U3, U4, and U5. And all these Qs are known for every ply. So Q on bar and all these quantities only depend on the angle theta. So with that, now this looks very messy, but if you recall, the fourth resultant is nxx, ny, nxy, and that's a summation of these little integrals of every ply added. You're basically adding up the integrals of all these plies up, and that's why you have a summation symbol. But this equals the integral minus h half to h half. The only problem is that stress varies from ply to ply, because as you saw, the stress depends on the strain, but this is varying from ply to ply because of the angle change. And so that's why we have to integrate it in the manner that we're doing it. Okay. So when I go here, I realize that this integral of ply kth ply has the sigma xy, sigma yy, sigma xx. This here is the Q bar matrix that we discussed times the strain matrix that we discussed earlier. And that's this. Are we done substitute stress for that? Now notice that this strain is a strain through the thickness of the whole thing. But we found earlier, and I welcome to pause the video and look at your notes, but we demonstrated that strain is equal to the mid-surface strains plus z times the curvature strains. So this is what we got there. And so I can go ahead now and integrate. So note that these quantities do not depend on z at all. These curvature quantities don't depend on z at all. So I can integrate. None of these quantities here in this integral depend on z. Okay, these quantities are independent of z, so that can come out of the integral. That integral only applies to these two terms, and so the integral of this becomes then zk minus 1, and the integral of z is basically z squared over 2, but evaluated at zk minus 1 and zk gives you 1/2 zk squared minus zk minus 1 squared. And so that's essentially your force resultant related now to the strains of the mid-surface and the curvatures, and I need a constitutive law to be able to relate that through. Okay, and notice that this force resultant is integrated through a thickness completely. Okay, we can rewrite it in different. Since this is very messy, we can write it in a different way. We can multiply this by this coefficient and call that the A matrix. So you can see here that multiplying this by zk minus 1, this multiplication here can be simply put as this summation here. So this summation here, so this times that summation there is this one here, basically. And so I can write this in this manner, A1, A12, A16, and so forth. And so that's your mid-surface strain, and then I have plus this summation, this multiplication times this coefficient here. And so that's that basically here at the bottom right. We call that the B matrix. This is called the A matrix, that's called the B matrix. And I can plug that in. And so then the force resultant simplifies to the A matrix times the mid-surface strain plus B matrix times the curvatures. Okay. So note now how bending of a plate, which will cause curvature, will then also cause in-plane forces in that plate. That is not normally the case for an isotropic material. This will go away for an isotropic material. And that's something that you could prove through working it out. And so what we found here then is a relationship of force resultants to the quantities that we have talked about earlier. So let me back up and remind you a little bit of those relationships. So these are the 6 strain components. These are the mid-surface strains. These are the curvature strains. So we have 6 components of strain. And what we've done is related those to the forces, to the force resultants. There's 3 of them, okay? The A matrix can be quickly calculated. You know the location of each ply, so you can calculate this quantity. You know Q bar for each ply. So you can then do this calculation fairly simply with a simple Excel sheet or a MATLAB code, which you'll be doing, by the way. So let me explain to you what's going on. So these are called the in-plane mid-surface strains. These are the curvatures. This matrix right here is called extensional stiffness. This one right here is called the bending extensional coupling matrix. And so the internal force resultants can be found by calculating the A matrix and the B matrix. And the A and B matrix can be calculated if you know all the ply angles and the material properties. So these are fully known. These matrices are fully known. So this relationship can be made. Now I want to go ahead and derive what it looks like for the moment resultants. For the moment resultants, again, this stress is equal to Q bar times the strain. But I have a Z multiplied, so that's why I have a Z times the mid-surface strain plus Z squared times the curvatures. Now I apply the integral again onto the Z and the integral onto the Z squared, and I get Z squared divided by 2, but evaluated from ZK minus 1 to ZK gets me to 1 half this quantity. And for the integral of Z squared, I get Z cubed over 3, and again, that integral then gives me z cubed minus zk minus 1 cubed. And so, again, this is fully known for a reply. This location of the reply is known, so you can calculate that coefficient. And so you can readily calculate these coefficients. And for simplification purposes, you quickly see that this times this is, we already calculated before. So this is exactly the same coefficient. And so this multiplication here times the 1/3 is new, and that's your bending stiffness. Okay. So here you can see quickly that the moment is equal to the moment resultants is equal to, and again, these moment resultants and force resultants are the ones acting your free body diagram, and these are the ones that react to external forces, as opposed to the typical stresses that you're used to. These are your new stress resultants that you want to focus on. And so, given the mid-surface strains, given the curvatures, you can then, and you know all this stiffness because you know Q bar for every ply, you know the ply angle, you know the location of the ply. So these calculations should be fairly easy to compute. So you can then relate the moment resultants to the strain, mid-surface strains, and the curvatures, which again are not dependent on the z direction anymore. They only depend on the xy. That's why we're developing these 2D theories to simplify the need to go into 3D equations. Okay, and so for the nomenclature, this beam entry is called the bending extensional coupling. This one is called the bending stiffness here. And again, these are mid-surface strains and these are your curvature. I can put everything together. So I have the force resultant, the moment resultant, and it looks as simple as this. And it looks scary, but it's not that scary. What we've done is gone from 3D to 2D. These are the mid-surface strains. This is the curvatures. And the A, B, and D matrices, all these can be calculated because you know the ply angles. And you know the properties of every ply. And so you can calculate then, and you know the locations of every ply. So these calculations are fairly straightforward. And with that information, becomes fully populated. For a given stacking sequence, for a given ply layup, you know A, B, and D. That's fully known. Now, let me go back and backtrack a little bit and remind you that the Q bar was calculated based on these U's, and these U's depend on Q, and Q is the same for every ply as long as I have the same ply material. So it's only Q bar only depends on the ply angle. That's all it depends on. So I can put everything to contracted notation for simplicity, but all I want to point out is that these two here are called the bending extensional coupling. This is the extensional matrix. This is your bending matrix. And why this is coupling is because when you look at the force resultant contains curvature terms, and it only contains curvature terms if the B matrix exists. The bending moment contains the curvature terms, but it also contains the stretching terms of the mid-surface, and only it exists because of this B matrix that's here. And again, A, B, and D can be fully calculated for a given stacking sequence. Given the stacking sequence, A, B, and D are known, fully known. And these are all numbers. It looks messy here, but these are all numbers. And so I want to use the governing equations of the plate because my ultimate goal is to figure out what are the governing equations for 2D. I know the governing equations for 3D. What are the governing equations for 2D? So I know the strains, which are as a function of deflection. So I can plug this in here. I know the curvatures. I can plug that here. Now I can take N and M, which are now in terms of U, V, and W. Remember, these are deflections at the mid-surface of the plate. Remember, I'm only tracking the mid-surface. I no longer have to track the whole 3D plate because I've already integrated everything through the thickness. So I can get the combined effect of the whole thickness of the plate. And so now I'm wondering, now I'm trying to figure out how to solve these equations, how to put everything into a governing equation. So these strings can plug in here, these strings can plug in here, these curvature strings, plug all these force resultants and moment resultants, which are the stress resultants. We have the three governing equations, plug all that in, and you get a mess. You get three equations that had U, V, and W as unknowns, in plane lateral deflections and out of plane deflections. In this case, I'm including the pressure. So you have basically a plate subjected to a pressure. So three equations, and the three unknowns are U, V, and W. The boundary conditions of a particular problem are known. So as you can see, these are highly complex problems to solve. You're probably not going to do that by hand. You will do this through finite elements. And the boundary conditions typically are going to change depending upon what you're looking at. So for a plate with simply supported boundary conditions, which are basically rollers at each edge, you're gonna have deflections are zero at those edges. For a clamped plate, you're gonna have a situation where the deflections are zero, but also the slope is zero. And here are some illustrations of various simply supported conditions you can have. So here you can see a W0 in the thickness direction because it's supported well and it's fixed to the ground. But you're allowing bending to occur at that pin. And you can see that U and V are also zero, so there's no deflection in X and Y. You also have this type of simply supported beam where it can roll in the X direction. So as a consequence, V is zero, which means that it cannot roll in the Y direction and it cannot move in the Z direction. But yet the bending moment and this load here are zero because nothing's resisting that motion. And likewise, I have this type of boundary condition, which is in the Y direction. It can roll in the Y direction, but it cannot move in the X direction. So as a consequence, U is zero, V is free to move, W cannot move up and down, and you then have the final boundary condition they could have, which is a roller in two directions. So you're used to seeing this for a beam, but for a plate it becomes a little more complicated. W is zero, but then U and V are free to move, and then MX, NX, NXY, they're all zero because nothing is resisting the motion. So three governing equations, very messy to solve, and I'm not going to make you solve them. It's not my goal is to try to explain to you what is going on, given the loading conditions they apply. So here's an external load applied, for example, the pressure. Given these boundary conditions that you have three equations, and the three unknowns are U, V, and W. And you should be able to solve for U, V, and W. Well, you shouldn't be able to solve it by hand, but using maybe a finite element code. So what is the solution procedure when you go to finite elements? And so if I go to finite elements, what is that solution procedure? The finite element analysis, and I'm not going to go into the theory of finite element analysis. If you're interested, go ahead and subscribe to my channel, and I have a whole set of finite element notes. But for this particular lecture, what is finite element analysis doing? We're discretizing the partial differential equations over the domain using smaller domain elements. As you can see here, solving these equations, three equations, look highly complex. But if I can try to solve it for smaller domain elements, I could get somewhere. And so if I were to have a finite element mesh, the finite element analysis provides you the ability of applying loads to a structure like an aircraft. And when you apply all these loads, it can then solve for these deflections U, V, and W that I talked about. And so it allows you to find those deflections in a way that's straightforward. Closed form solutions can also be performed, and I may cover a few later. But the bottom line is that a finite element analysis is the approach that you will use to solve these equations. And so, given the loads and boundary conditions of the problem, what we really want to do is to determine whether the structure I design can survive the loading environment. And so what I want to be able to do is determine the laminar strains and stresses in each layer along the material principal directions, because it's along those directions I really have the strength information, the strain to failure information that we had discussed earlier in time. And so given the loads applied to an aircraft or a plate or a spacecraft, I will then use these equations over the whole domain and solve these highly complex equations for U, V, and W, but use finite elements to do it. And the idea is then ultimately what I want to do is once I know U, V, and W, find out what are those strains and stresses along the material principal directions? Because that's where I have data for in terms of what's going to fail. So, what is the solution procedure? Once I know U, V, and W from these three equations, I can then plug it in here, U, V, and W. Okay. So I have UV, and that will give me the mid-surface strains. Once I know W, I know the curvature strains. So I have these three. So these six, I'm sorry. Once I know the mid-surface strains, once I know the mid-surface the curvature, right? If I know the mid-surface strains and the curvatures, I can calculate the strains at any point through a thickness using this equation. Okay. And I know what is a strain at every ply because I know the mid-surface strain, I know the curvatures, and I know the location of that ply. So I can calculate that mid-surface strain. Once I know the mid-surface strain, I can then calculate, use the transformation equations we had previously discussed, and back engineer what is the strain along the material principal directions. Because this is really what you're going to use to calculate where, you're going to calculate whether you achieved failure or not. Again, the transformation matrix was given this before and varies upon what ply you're looking at. So that's why it's important that you track this as well. This changes from ply to ply. So in other words, I saw for UV and W, and that's the same. UV and W is for the mid surface of that plate. But yet I can get the 3D distribution through a thickness using this equation, right? So see how we've simplified the problem. Otherwise, you will have very complex equation with partial Z and all that. We got rid of Z, and that's why there's a 2D plate theory, classical plate theory, to be more exact. And so once I've calculated UV and W, calculated mid-surface strains and curvatures, which will be the same, that doesn't change. And now I have ply number 55. Well, find where that happens, where that Z occurs. What is the location of that ply? That's what Z is here, is the location. Once I have that, then I have the strain for that particular ply in the global material, in the global system, right? And so once I have that, I can use a transformation matrix and get the strains, but the transformation matrix corresponding to that ply angle, alpha, and then you can get the strains in the material principal directions, which are very useful to calculating, comparing against strain to failure data. But what if you don't have strain to failure data? You still can take that information, plug it in to your constitutive matrix. Q times strain gives you the stress for that particular ply in the material principal direction. Can also look at, so I'm able to find that, but you could do it differently. You can calculate the strains first in the global system, plug that into this equation, then get stress in this way, and then transform stress to get stresses in the material principal orientation. So there's two ways to do it, but this is one way to do it, the one I showed you here. But this one also works well. Okay, so let me go through and discuss what is going on when I spatialize it for various laminates and I simplify it for various assumptions. I think that's worth covering at this point. So we'll look at a generalized symmetric laminate. It's preferred for design, it's simple, and the nice thing about this type of design is that you get no coupling. So if you were to apply stretch into the plate, it won't bend as much. You're going to have some bending typically because not everything is perfect. But what is a symmetric laminate is what, and I discussed the types of stacking sequences we can have. What I want to do is connect that to what happens to the ABD matrices. And so when I talk about symmetric laminate, I talk about a minus 25 that's mirrored about the XY plane, and you get it also on the other side. And you see that with the 35, the 0, and the 90. As the number of ply increases, regardless whether you have a symmetric stacking sequence, if your plies increase, the number of them increase, this B matrix will approach 0. Okay, so that's another point I want to make. Antisymmetric laminates are such that the top half mirrors, but the angles are the negative, and you can see that here. So you're going to see that these quantities are 0, and these quantities will be 0. So there's no bending twist and no extensional shear coupling. So you don't have these components right here in the A and D matrices. And feel free to pause the video to study what is going on. And I think you will see here that these two right here are not contributing to the calculations of the force resultants and these two are not contributing to the calculation of the moment resultant. You also have antisymmetric cross-ply laminates, so that's 90 and zeros, and you'll find that for those situations, most of these are zero, except for few of this. Okay? Angle ply and no 90-degree plies are basically antisymmetric angle ply laminates with no 90-degree plies. The top half mirror is a mirror image of the bottom half, except the ply angles are the negative of the bottom half, and there are no 90-degree plies. In those situations, these are zero and these are zero. You also have balanced laminates where you may have a situation where a 30-degree ply also exists with the stacking sequence as a minus 30 degrees. Doesn't have to be symmetric or doesn't have to be a mirror image, but you do find these situations. In those situations, you only get no extension shear coupling. Quasi-isotropic laminates are interesting laminates. In the in-plane orientation, they provide you isotropic behavior. And I already discussed quite a bit that quasi-isotropic laminates may not always be the most suitable ply stacking sequence because you're going to get isotropic properties in the in-plane direction. And the whole goal of using laminated composites is to ensure that we are tailoring them to get the maximum performance we can for these types of laminates. So quasi-isotropic laminates can be identified as 0 plus minus 60, which is shown in the bottom left, 0 plus 45, 90, which is here in the center, 0 plus minus 60 plus minus 30, 90, that's this one here, or the plus minus 22.5 degrees plane weave, for example, will have that. How can you identify whether you have a quasi-isotropic laminate? If in your stacking sequence you have the same number of fibers going at an equidistance angle. So here I will have, like, say you have three paths going that way and so forth, then you have a quasi-isotropic laminate. And so that's going to give you an isotropic behavior in plane, and these two will be zero, and then these two will be zero for bending stiffness. We can go through cylindrical bending strip theory to kind of illustrate what the solution of that would look like. And you're going to encounter that sometimes. So in cylindrical bending strip theory, the derivative with respect to y vanishes. Out of all those equations I showed earlier, which were quite complex, the three equations simplified to this for cylindrical bending. And they look very similar to bending equations that you may have seen in school. For example, this equation should look familiar for mechanics of materials. This will be typically EI, W4 primes, and that's equal to the force applied. So that looks very similar to bending of a plate. Okay, and in fact, we can prove to you, and you should be able to demonstrate this, that D11 is basically 1 over 12 BH cubed times E. So you basically get the same EI type term that you will have gotten through the equations from mechanics of materials for beam under distributed loading. Here you have additional terms, and it's quite understandable because we have a more general formulation. Let me show you the solution, a simple practical solution, closed form solution of a simply supported plate subjected to loading. And the reason this is a good example is because we can actually solve it exactly. So this is a simply supported plate where each edge is allowed to rotate and is subjected to a uniform pressure. So if I look at a laminated composite, symmetric and balanced, so there's no bending, stretching, and you don't get any B matrix, and a lot of these terms go to zero. And so that I want to solve it for a very simple problem, a symmetric balanced laminate, so that we can actually solve it. So there's something called the Navier solution. Now, I don't want you to get stuck in the math, but understand that there are some solutions people have developed to solve equations like this one. And so one such equation is called solution is called a Navier solution, which assumes a summation series, infinite series for the deflection. And you have these coefficients that you need to find, and sine alpha x, sine beta x. Alpha is given by this MPA is the dimension of the plate, B is the other dimension of the plate, and M and N are being varied from 1 to infinity. Okay, so if you look at this carefully, A is known, M pi, and N pi is known. So all these things are known, and so I'm trying to find that coefficient. The beautiful thing about this is that it automatically satisfies the boundary conditions at x equals 0 and y equals 0. We don't want the deflections to be, we want the deflections to be 0 at the edges of this plate, which is subject to think of this plate subjected to pressure, right? So these edges are pinned and deflections out of plane are not possible. Well, this does a good job. This solution satisfies that. And you can check that when x is 0, this is 0, so then all this is 0. And you can also see that when x is a. When x is a, you have a there. A cancels a, so sine of m pi will give you 0. The moment also 0 at those boundaries, which this would be 0 because I'm not clamping it. And so you can also verify that I get moments to be equal to 0. Because I have second derivatives that need to be calculated, and the second derivative of sine gives me sine again. So when I evaluate sine at the edges of that plate, I also get 0 again, which is exactly what I need for a plate that's pinned, simply supported. So I don't have a moment at those edges as a consequence that will react the fact that's pinned. And so the transverse loading condition can be expressed as this. If you look at a more advanced math book, QMN can be given by that. So if I have a distributed load Q that's, a distributed load Q of some kind, it could be uniform, whatever it is. If it's uniform, then this is a very easy integral. Whatever it is, this QMN, this distributed load can be represented in this manner. And QMN looks like this. For uniform load, you will put, let's say, 1 pound, 1 psi. You put 1 psi there and integrate this. Then you can substitute this Q here and this W here into this governing equation. And when you do that, you get this interesting equation. Okay. Now, for this equation to be true, parenthetical has to be equal to 0. And so I can solve for WMN in this manner. And so what in fact I've done, I've solved for the deflection of the beam, because that's exactly what I was looking for, not the beam, but the plate. I'm able to find an expression for the WMN, which is the coefficient here. And so if I have that, I can now plot the deflections of that plate very simply. Note that any transverse loading can be expressed in this manner. For uniform loading, this turns to be, QMN turns to be a simple form. For point load, it's going to look like this, and so forth. Bottom line is that once I know WMN and I know W, the deflection, and note that this QMN is not the constitutive law, this is represented loading environment. Once I know the deflections, since in this problem we don't have any mid-surface strains because it's all bending that we're looking at, I find the deflections out of plane, which are given by this, and then I can look through what location of the through a thickness I want to find the strains. Once I have that, I plug into the constitutive equations, and for a balanced symmetric laminate, these are 0, and so I get the stresses corresponding to that particular laminate, not in the material principal orientations, but in the global orientation. But I can, in fact, find it for the material principal orientation by using the transformation matrices that we had discussed earlier. I can also solve simply supported plate on two opposing edges. Here's an example of that. People have solved this type of problem in the past. You assume that these two edges are the ones simply supported. These two are free. That makes the solution a little bit more complex, but it can be done. And so let's examine this particular problem, which becomes a little more complex. So again, the same type of situation, symmetric balance. And so we're gonna, all these terms go to 0. So we're not considering those. But in this case, we're going to use something called a Libby solution. And he chose the following form for this deflection. He said, okay, I'm going to make W a function of X. So I don't know what that function is. But in the Y direction, I'm going to assume a sine function. And so that makes perfect sense, because if you look here, in the X direction, W may vary, and we don't know how that looks like. In the Y direction, sine seems to be a good assumption that will satisfy the boundary conditions. You can see that it's automatically satisfy the boundary conditions at y equals 0 and y equals b. When y is 0, this goes to 0. And when b is 0, when y is b and b cancel out, sine n pi gives you 0. And you can see there quickly that w is 0. You can also see that makes sense, because in this plate, these two edges are simply supported. I apologize. And now the moments at those edges are also 0, and you can see that this formulation also gives you this solution, this form of the solution also gives you that. And again, I'm not asking you to memorize these solutions because you're not going to use them in the industry. But what I'm trying to illustrate is how loading on a plate plays out in a 2D type formulation. If this was 3D, if I did not make the simplification from 3D to 2D, I will not be able to go through this process. So it was only because I made that simplification is that I can solve these equations using plate theory. I can take any transverse loading and express it from this manner, where Qn is this. You can substitute these expressions back into the governing equation right here. That's your governing equation. And once I plug it into the governing equation, for now I have this fourth order differential equation. And so now I can solve for Wn, and that will be a fourth order governing equation you can solve. Use the boundary conditions to solve for Wn. You can let Mathematica do that, wolframalpha.com, or a solver that gives you differential equations. The bottom line is you can solve for Wn. And now you can just follow the same process we discussed before. Once I know Wn, I know the deflection. Once I know the deflection, I can go ahead and calculate the curvatures. Once I know the curvatures, I can get the strains through a thickness at any point through a thickness, at any ply, and then I can get the stresses in every ply. And if I want to get that in material principal orientation, transform them using the T matrix, the transformation matrix. So that explains how to approach that. And now what I want to cover, so in the previous lecture, video lecture, we covered how to get the 3D effective laminate engineering constants. But now what I'm going to cover is how to get the 2D effective laminate engineering constants. Now this particular part of the lecture is required in your homework. You're going to have to do this and then compare against efonda.com. There's few websites that can get the ABD matrices for you. So similar to 3D theory, sometimes it's convenient to calculate the effective engineering constants for 2D plate. This is a good idea to do if the laminate is symmetric. If not, then you're going to have some issues working it. And so if the laminate is not symmetric, then it may not work out as well. Since the laminate is symmetric, the B matrix is 0, and so the force resultant equals A matrix times the strain, the mid-surface strain. I can solve for the strain in this manner, okay? And A star here is the inverse of A. And what I'm going to do, I'm going to do a little trick. I'm going to multiply by T every row and then divide by T on the end. And so if I do that, now N divided by T gives me the average stress in that particular ply for the X direction, Y, and XY. Because remember, N was integrated through the thickness, but I'm trying to get an average quantity there. So N divided by T times 8 times T, the T cancels out. That gives me exactly what I got here in the bottom right. But because the strain in the global orientation is this, the stress in the global orientation is this, I could say that the compliance of the plate in the laminate coordinate system will have elastic constants that look like this. You could pretend that you have a material, like that block has a bunch of plies. Just assume that block is a particular material. And so that material has to follow a relationship like this. So all you have to do is compare this coefficient to that, and that's going to give you the modulus, but in the global orientation system. It essentially gives you, say you have a 0 plus minus 40, 60, this EXX bar represents the modulus, the effective modulus in the X direction of the whole stack. The same for the Y, and so forth. You can also get the Poisson ratio and quantities that look like Poisson ratio, but all they do is connect the stretch quantities with the shear quantities. So let's discuss a little thermal effects next. So how to account for thermal effects? So to account for thermal effects, composites generally solidify at a temperature much higher than room temperature. So when you cool down from cure to room temperature, cure is the point at which the structure solidifies. To room temperature, it will lead to residual stresses caused by the differential thermal contraction between the layers. The operational stresses at temperature colder than room temperature can increase the thermal stresses. So it's important to understand that if you have cooler temperatures even, then the thermal stresses will increase. How do you account for that? So thermal expansion is a material property that governs the behavior of the material during thermal loading. And I apologize for that. And so the stress-strain relationship is given by this. So, but now we're including the expansions, the coefficient of thermal expansion. And we're going to take the reference temperature as the temperature at which the composite solidifies for the reference temperature. So we can apply the same transformations we talked about before to transform strain to stress, but bring that into the global orientation system. And so this is what we get for that. The alphas here, these alphas can be also transformed using this relationship here. So you can just use these formulas and you'll be fine. So alpha in the global orientation system can be related to the alphas in the principal orientation system. You get this weird alpha XY that shows up, but it's important to consider. Okay, so once you have alphas, that can be plugged in here, and now you're ready to go. So the laminar stress resultants, again, use the same formula we had before for the force resultants, but now that integral is broken up into all these plies, just like before, but now the stress, right? Not only you get the stress equals Q times the strain, but now you have the strain we had before, but now we have to account for the coefficient of thermal expansion that we had discussed previously. So this is a new term that this column vector you had not seen before. And so again, I can multiply everything out, but the new term here is this matrix multiplied by this here. This is new. So that's your force resultant due to thermal stresses. Okay. So this is purely caused by thermal stresses alone. Hence, very similarly, if you do it for the moment, you're going to get something like this. So hence, you're going to get the force resultant and the moment resultant to be the matrix we had before minus the force and moment resultants caused by these thermal stresses, the thermal environments, I'm sorry. And you can see that from here. So we can also define an effective coefficient of thermal expansion. You can do that too by using the laminate midplane as follows. So you can say, okay, this is my effective coefficient of thermal expansion times delta T. That's your bit surface strains. Okay. And for symmetric laminate, and only considering in-plane thermal forces and no mechanical forces, so just in-plane forces, no mechanical forces, then your thermal force resultants become this quantity here. Okay, so nothing has really changed from what we discussed. And so then you can calculate the you can substitute mid-plane strains as we discussed before. So that's this term right here can be incorporated into this column vector, right? Because if the mechanical forces are zero, so that's this column, then and the B matrix is zero, then I can solve for n. And so n is A times this column vector times is equal to delta T times this effective coefficient thermal expansion, which I'm trying to find. And I make that equal to this because epsilon was found to be that. And so for if I assume a uniform temperature through a thickness, we can solve for the effective coefficient of thermal expansion. I can do that. So for uniform temperature, then I can solve for that by inverting this matrix, okay? And delta T cancels out. So inverting that gives me this quantity, and now I can get the effective coefficient of thermal expansion for the whole stack using this formula. So given the coefficient of thermal expansion for a reply that's transformed in the global orientation, multiplied by the Q matrix, multiplied by the A matrix inverse gives me the effective coefficient of thermal expansion of the whole stack. Hygrothermal effects can also be included. Hygrothermal effects are moisture effects where it causes a composite to swell and it can cause strains and stresses in the plies. So moisture absorption, by the way, can cause reduction in strength, just like the thermal can. And the coefficient of thermal moisture expansion is usually indicated as beta, similar to alpha. And the coefficient and the moisture concentration is usually called T. So similarly to the thermal expansion transformations, this is what you get for the moisture expansion transformations. The hygrothermal force resultant becomes this, and so this is what you will get. The hygrothermal moment resultant will become this, and it's important to note that these are caused by the concentration of moisture. Beta is known, that is a measured quantity. So these two things alone will cause this N and M to occur. And so then, if you include thermal and hygrothermal effects, these quantities will be fully known. And in the finite element modeling, you can apply all these thermal and moisture conditions and mechanical loads, and then determine the deflections. And from the deflections, again, you can then solve for the apply stresses and strains, as we discussed earlier. An example. So the solution procedure is provided a second sequence of the laminate, the lamina engineering constants, and the cure temperature. We want to find out the residual stresses in each ply at room temperature. So given the cure temperature, what is going on at room temperature? So obviously, because I cured it at a hotter temperature. When I cool it down to room temperature, residual stresses will appear. The first step is to calculate the ABD matrices for the whole laminate. So you get the whole thing. Once you get the whole thing, you can. There's no hygrothermal effects here, so don't worry about that. There's no mechanical load in this case, so you can ignore that. I can now calculate the coefficient of thermal expansion in the global coordinate system, and that depends on the ply angle. Okay, so that depends on the ply angle. Alpha 1 and alpha 2 are in the material principal orientations. And so once you have this information and you have delta T, you can then calculate the force and moment resultants due to the thermal loading that was applied. So this is zero, this is known, and this is known. So you can solve for the mid-surface strains and the curvatures. Once you determine these mid-surface strains and curvatures, you have the coefficient of thermal expansion times delta T, calculate the strains in each layer, and the strains in each layer then is used to calculate the stresses in each layer in the global orientation system. And then from there, you can transform this to get the stresses in the principal orientation system, material principal coordinate systems. You can also do that with the strain. You can transform the strains from the global to the local orientation system. And here's some typical material properties that you can find for various material systems. Feel free to pause the video and look at this carefully. But I hope through this video lecture, in summary, what we've done, we've learned how to take a 3D problem and use classical plate theory, which is making fundamental assumptions about assuming that the plate will be thin, that if I were to make it thin, I can just track the mid-surface. And if I can solve for the deflection of the mid-surface, then I can solve for the ply stresses and strains, which are important to determine whether the structure will fail or not. That's how you will size it, right? You want to size it to make sure you're not failing the structure. So thank you very much for following this. I hope that you enjoy the show, that you can take a little bit of self-study and go through all these materials on your own one more time. And I ask you that you spend that time very carefully. And I'll see you next time. And have a great time and stay safe.